Greetings students, my name is Amit Bhosle. I am currently associated with the Department of Hydro and Renewable Energy, IIT Roorkee. So having understood about the different forms of energy, need for hydrogen energy, different production methods of this technology, let's get more into this field and try to understand through thermodynamics. So moving on, all of us know how IC engine works. Basically, it's a cylinder and piston arrangement here, and what we typically do is we try to send the fuel and oxidant, that is O2, in the cylinder. So when it gets combusted, we have this reaction fuel plus O2, which gets converted into thermal energy, and of course the byproducts depending upon what fuel we are using. So if I replace this fuel with hydrogen, we can also expect a similar reaction taking place in the cylinder. We will again have thermal energy released, which will be converted into mechanical energy, and then ultimately that is how the engine runs. And of course the byproduct will be, in this case, will be water. Let us balance this reaction up. So if, in other words, if I have hydrogen and oxygen in the cylinder, it will also be able to produce this thermal energy and the byproduct water, and we can run the engines on this. So if I generalize how this reaction takes place and what are the different conversions that take place through this piston cylinder arrangement, we have chemical energy, which then gets converted into the thermal energy, which again gets converted into mechanical energy, and if needed it can then be again be converted into electrical energy also. So chemical energy, as we all know, it is a high grade energy, and mechanical energy is also high grade energy. Let me abbreviate this, high grade energy. However, thermal energy being the low grade energy, the total conversion efficiency of this process is less than, I would say, 30% at max, and this is again limited by Carnot cycle, as we all know. So this is the main drawback of, you can say, combusting the fuel and again be converting it into the different forms of energy. So this is where the electrochemistry comes into picture, and it can overrun the conventional conversion form of this system. So how does it work? Let us slightly understand that. So if I try to see what is happening between the reactant species, that is hydrogen and oxygen, which gets converted into some form of energy, I will put as energy, and plus water as a byproduct. So there is a transfer of electrons between these reactant species, which basically released as a energy, and of course the byproducts. So the question arises is, if I catch these electrons, force these electrons to move through an external circuit, will that give us then electricity? Answer is very yes, and that is what is being done in the field of electrochemistry. So in short, if I put an electrode here at the respective gases, and with some arrangement I force this electron to move through an external circuit, the one or the other half of the reaction is complete, or we have taken care of it. However, if you look at the hydrogen as an atom, it has one proton and one electron in the external circuit. This is electron. So we have taken care of the transfer of electron through highly electrically conducting or conductors. However, this proton also has to be transferred from one side to the other, and then only the reaction that I have mentioned will be complete. So we also need highly ionically conducting material. In other words, we also need electrically conducting materials and we also need ionically conducting materials, and this ionically conducting material will be put up in between these two electrodes which are electrically conducting, and the ionically conducting or ionic conductor will be put up here at the center. So, these two electrodes and I will write plus one electrolyte. This is called as electrolyte, which is ionically conducting. These together form electrochemical system. Electrochemical or electrochemically active system. So, if you take an example, fuel cells or electrolyzers, batteries or capacitors, they are all examples of electrochemical systems. So, before we get into more details of this, let me also recommend a few books for reference. We can very well use, let me write books. First one is Fuel Cell Fundamentals, by Riano Aire and group. There are a few more authors for this book. Second, we can also read and refer fuel cells, principles and applications by B. Viswanathan and M.A. Scibio. Third one, we can also refer electrochemistry by Alan Bard and Faulkner. And of course, there are many more books available. We can read and go through any book that authors may like. So, moving on. So, let us quickly understand the history of fuel cell. So, it was basically in 1839 when Sir Grove invented this alkaline fuel cell. Basically, we will see what alkaline fuel cell is and how it works. Invented fuel cell, and this was when it was conceptualized. And of course, back in 1889, basically this concept fuel cell, this term was coined by Mond and Langer. And of course, there were then few more inventions, additions to this technology, and however, things really started seriously when in 1959, when NASA used a stack of alkaline fuel cell in one of their space applications. And that is when the entire world got also interested in this technology, and then things started rolling up. What are different applications? We can use these fuel cells in many applications since it is a source of energy. So, we can use it in stationary applications. We can also use in automobile application. We can also use them in space applications, and so on and so forth. So, if I simplify what are fuel cells, if someone asks us what are fuel cells, you can say fuel cells are like a, you can say, a black box wherein fuel and oxidant are supplied, and their chemical energy of this reactant species is converted into electrical energy. So, you can see this is like a black box. Now, the entire course is all about what happens in this black box. So, this is what we will understand. So, fuel cells, as I said, it's a converts the chemical energy of gases directly into the electrical energy or electricity. Please be informed that this electricity or electrical energy that we are talking about is a DC. There is no so we get direct current through this fuel cells, and of course we, along this with electricity, we also have the byproducts. Depending on what fuel we use here, if you have the hydrogen, then byproduct is water. If we have different fuels used like methanol or ethanol, then the byproducts will also change. So, if I try to elaborate as to what happens in this black box, let me draw a schematic. So, as we have already seen that in fuel cells we typically have two electrodes and one electrolyte. So, this is your electrode 1, let us call this as anode. We will see why it is called as anode, and this one as cathode soon, and this is your electrolyte. Let me write it as EL. And when we supply hydrogen, here and let us say oxygen on this side, so there are different reactions take place, and on this side, on the anode side, we have hydrogen getting split into protons and electrons. So, 1 mole of hydrogen gas is split into 2 moles of protons and 2 moles of electrons. So, only protons pass through this electrolyte, as it has already been mentioned that electrolyte should be highly ionically conducting, and it should be theoretically should be zero conductor or insulator for the electricity or electrons. So, only protons pass through this electrolyte. What happens with these electrons? Since there is a sea of electrons that gets generated here on this electrode, they have a tendency to move out. This is the electrons, and that is why this electrode is called as anode, because there is a loss of electrons taking place on this side. So, electrons travel through the external circuit, that is where we get the current, or rather electricity or electrical power. And on cathode, since this electrode is receiving the electrons, there is a reduction taking place, and that is why this electrode is called as cathode, where the oxygen combines with, or let me say, these protons and electrons to form the product water. Let me balance this up, half mole of oxygen. So, this is your reaction at anode, this is the reaction at cathode. So, the complete reaction or the net reaction is, as we have written earlier, it is H2 plus half O2, that gives water. So, if we club this reaction and this reaction, the net reaction will still be the same. So, these reactions that is occurring at anode and cathode, they are called as half cell reactions. So, this is how a fuel cell looks like, and this is how it works. Of course, I have not shown the different auxiliary components that are used in fuel cell. I have only focused on electrodes and the electrolyte. So, this is with respect to the electrodes and electrolyte. However, we should understand that all these fuel cells or electrolyzers, they are always classified with respect to electrolyte that is being used. For example, if you use a solid polymer as an electrolyte, it is called as proton exchange membrane fuel cell or proton exchange membrane electrolyzer. If we use alkaline solution, it is called as alkaline fuel cell or alkaline electrolyzer. So, we will quickly see how these cells work. Let us first get with the alkaline fuel cell. So, the chemistry is slightly different, as we can see. Let me redraw it. So, we have this anode and cathode, we have hydrogen and oxygen being supplied on the respective electrodes. Now, please understand this electrolyte is an alkaline solution. Typically, it is, in case of alkaline fuels, it is around 1 molar potassium hydroxide. And what happens is, here for the anode we have H2 plus this, there is OH minus ion that basically shuttles between the respective electrodes. So, we have 2 moles of OH minus, which then get converted into 2 moles of water and 2 moles of electrons. This is what happens at the anode. At cathode, we have half mole of oxygen plus 2 moles of electrons that convert into 1 mole of water plus 2 moles of OH minus ion. So, if we look at the net reaction still remains the same, which is H2 plus half O2, that gives H2O. So, here like we have seen earlier, the proton shuttles between anode and cathode, whereas in case of alkaline fuel cell we have this OH minus basically shuttling between the electrodes. So, this was the same cell that was used first by NASA. Like I said earlier, NASA was the one which basically used the stack of alkaline fuel cell and they used it in one of their space applications. So, what are the advantages that we get? Advantages is a very low cost fuel cell, because we do not use or we do not need to use any platinum based catalysts here. We can also use like nickel or the other low cost materials as catalyst can be used. This is the main advantage of using alkaline fuel cell. So, we have this, the same stack of fuel cells was used first by NASA back in 1960s as mentioned earlier. So, what advantage it offers is basically we can use like a nickel based catalyst, which are low cost catalyst, and we do not need to go to platinum based catalyst in this type of fuel cell. What drawback or disadvantage it has is it has a very low tolerance towards carbon dioxide, as carbon dioxide when it gets into the cell, it forms carbonates, and that ultimately leads to lower performance. And this is one of the big drawbacks with the alkaline fuel cells. We have already, this was the first one, second one we have also gone through this. Let me put on membrane fuel cells. They are also abbreviated as PEMFCs. The PEMFC is also called as polymer electrolyte membrane fuel cell or polymer fuel cell. We have already seen how these fuel cells work. So, let me go through it one more time. This is hydrogen and oxygen. We have, in this case, electrolyte is a solid polymer. So, as we can see, this hydrogen, the anode reaction is still the same. Hydrogen gets split into 2 moles of protons and 2 moles of electrons. At cathode, we have this protons shuttle and electrons move through an external circuit. So, once they reach the cathode, at cathode this half mole of oxygen combines with 2 moles of protons and 2 moles of electrons to form the product water. So, this is how the proton exchange membrane fuel cells work. Now, if you look at the net reaction here as well, the net reaction still remains the same, H2 plus half O2, that gives H2O. So, here also in case of alkaline fuel cells, we have similar net reaction with respect to the proton exchange membrane based fuel cells. Only the half cells reaction sort of change in some cases. In most of the cases, the reactions remain same. The advantages, as we can see, advantages is very simpler in construction. It's very compact. I would say a simpler construction that ultimately leads to compact device, and it has got a very high performance. Performance is better. What are the drawbacks or disadvantage? The cost. Cost is more because the catalyst that is used in this type of fuels is typically they are platinum group elements. So, either platinum or palladium catalysts are used in this kind of fuel cells, so which ultimately leads to the cost. And this polymer is also is slightly costly and in this kind of fuel cells, so that adds to the another cost of this fuel cell. So, let me go to the other one, the third type, which is called as phosphoric acid, PAFC, phosphoric acid fuel cell. Let me write phosphoric This is also very similar to what we have studied just now. It is very similar to that of proton exchange membrane fuel cell. The reactions are almost similar. So, we have hydrogen and oxygen, and this is electrolyte. In this case, it is a phosphoric acid based dipped electrolyte, and anode and cathode reactions remain the same. H2 gets split into 2H plus 2 electrons, whereas in case of cathode, it half mole of oxygen combines with 2 moles of protons and 2 moles of electrons to form product water. So, what are the advantages? Yeah, before I forget, this as fuel cell typically operates at 150 to 200 degrees Celsius. This is its operating temperature. The other two types that we have seen earlier operate at low temperature around 60 to 70 degrees Celsius. So, what is the advantage that this cell offers at high temperatures? Because it has got good tolerance towards the carbon monoxide, and which, in other words, what it implies is we can use hydrogen which is produced from the conventional sources, for example, steam methane reaction. So, we do not need to separate out the carbon monoxide and dioxides, and we can straight away supply this hydrogen to this kind of fuel cell. So, this is the just brief of different types of fuel cells. We can summarize this, how these fuel cells are classified. So, let me summarize this classification of fuel cells based on the electrolyte use and the operating temperatures. So, we can do it this way. So, these are the anodes and these are the cathodes, and this is the electrolyte. So, we have H2 giving, this is your anode, this is the electrolyte, and this is your cathode. So, what is the settling ion here? It is H plus, that is proton, which moves from anode to cathode in case of PEMFC, which typically operates around 70 degrees Celsius. This is your temperature, this is your type. So, why this is called as PEM fuel cell? As we have mentioned earlier, the electrolyte is basically proton exchange membrane. It is a solid polymer that we have used. In case of alkaline fuel cell, it is H2 and O2. The OH minus basically shuttles from between cathode and anode. So, basically OH minus goes from O2 to H2. So, this is alkaline fuel cell, which also typically operates at 70 degrees Celsius. Then we have high temperature fuel cell, so H2, and here O2, we have H plus ion shuttling between anode and cathode. This is high temperature PEM fuel cell, which typically operates around 150 degrees to 200 degrees Celsius. Then we have molten carbonate fuel cell, wherein we have CO plus shuttling between H2 and O2. So, this is called as molten carbonate fuel cell, which typically operates at around 650 degrees Celsius. And then we have solid oxide fuel cell, wherein H2, and here we have O plus going from cathode to anode, and we have, this is called as solid oxide fuel cell, solid oxide fuel cells, which is also abbreviated as SOFC. So, typically it operates around 1000 degrees Celsius. So, these are the classifications of fuel cell. As we can understand, all these fuel cells or electrolyzers, in other words, in other cases, they are all classified based on the electrolyte that is used. So, if we are using solid polymer, it is a proton exchange membrane based fuel cell. If it is alkaline solution, it is alkaline fuel cell. It is molten carbonate, then it is as an electrolyte, we can say it is molten carbonate fuel cell. If a solid oxide is used as an electrolyte, it is solid oxide fuel cell, like that. So, similar is the classification with electrolyzers as well. This becomes proton exchange membrane water electrolyzer. This becomes alkaline electrolyzer. This is high temperature PEM based water electrolyzer. This is molten carbonate electrolyzer and solid oxide electrolyzer. All these fuel cells and electrolyzers are classified with respect to electrolyte. So, before get into the thermodynamics of these systems, let us understand the molar quantities, as that will be used in our majority of our discussions. So, we have intrinsic. I am sure the readers might have gone through this thermodynamic specific terms. Intrinsic quantities, they are the basically ones that do not depend on scale or mass. And we have another term called as extrinsic quantity, which basically depend on mass or scale. So, coming to intrinsic quantity, what are the examples? We have pressure, we have temperature, and then we have density, etc. We can also write enthalpy, the complete enthalpy, which is denoted as delta H. We can also go with the other thermodynamic terms such as Gibbs free energy and entropy as well. Extrinsic quantities depend on the mass or scale. So, obviously mass will be the first example of extrinsic quantity. We can also go ahead with the, by mistake, this should be on molar basis. These are all quantities based on the molar quantities. So, if I write these terms again, this will become delta small h, this becomes delta g, and this becomes delta small s. So, smaller representations of these capital things basically mean they are all intrinsic quantities or on molar basis. Coming to extrinsic quantities, the same terms can be written like this. So, delta H or delta G or delta S. So, when we write capital letters, that means there are extrinsic quantities that depend on mass. The entire mass is basically taken care into in this terms. So, this is what we will be getting through most of the times, and let us write the reactions. We have write for enthalpy. Enthalpy of any reaction is basically H equals U plus PV. So, let me write this as equation 1, and let us differentiate this. dH equals du plus P dV plus V dP. So, this is my equation 2. So, what we write from first law, of thermodynamics, what we understand is dq is equal to du plus E dV, which we also can write as d ds. This is my equation 3. So, when I write from equation 2 and 3, what we get is dH equals d ds plus V dP. Please understand, this pressure P is written, it is a small letter because it is an intrinsic quantity. So, since all these fuel cells or electrolyzers, they operate at constant pressure. So, at constant pressure, so this V dP term will be moved away. So, we can write V dP is equal to 0, as since dP is equal to 0. So, we can write dH equals dS, which is equal to dQ. So, it means that enthalpy is same as the heat transferred in the reversible process. That's a very important conclusion that we can draw. So, since it is equal to the TdS or is equal to dQ, so it is the same heat that is transferred to the in a reversible process. So, we can equate enthalpy and the heat. So, which means that enthalpy is the same amount of heat transferred in a reversible process. So, with that we will stop here and we will take on with this same expressions in the next class. Thank you.